Hello and welcome to the Unit 5 Section 4 video on the applications of similarity. So in the last section we started to kind of get into a couple of the places where we can apply similarity. We did the perspective drawing. A little bit earlier in the unit we did the scale of the boxcar. Here we're going to talk about what are some specific things that we can use similarity for in the real world. And the first is going to be indirect measurement. Indirect measurement is any method that uses formulas, similar figures, and/or proportions to measure an object. In a lot of cases, we have an object that is just too big to feasibly measure using a tape measure. Okay, it's just not practical. But there are other techniques that we can use to do that. So in this first example, a student wants to find the height of a statue of a pineapple in Nambour, Australia. She measured the pineapple shadow and her own shadow. The student's height is 5 foot 4 inches. What is the height of the pineapple? So the first thing we're going to do is convert the measurements to inches. So starting off with the measurement to inches, we are going to take the measure of AC and we are going to set that equal to 5 foot 4 inches. Okay? That is the height of the person. Well, we're going to convert that to inches only. So we're only working in one unit. So there's 12 inches in a foot, so 5 times 12 plus the 4 additional inches gives us 64 inches in total. Now let's take a look at the height, or I should say the length of the shadow for the person. Well, the length of the shadow of the person, which is BC, is 2 feet. If we take those 2 feet and we multiply it by 12 inches per foot, then we get 24 inches. And then finally, for the length of the pineapple shadow, that is 8 feet 9 inches. If we take 8 feet, multiply it by 12 inches, and add the additional 9 inches, that's going to give us 105 inches. So now everything is in the same units. It's all in one unit, and that unit being inches. All right, so now we need to find the similar triangles. Well, because the sun's rays are parallel, then we know that angle 1 and angle 2 are parallel. Additionally, since we know that the shadow to the person and the shadow to the pineapple make a 90-degree angle, that's a second angle that is the same. So we know that angle 1 and angle 2 are the same. We know the 90-degree angles are the same. So therefore, triangle ABC is similar to DEF by angle-angle similarity. Now let's find DF. So since we know that the triangles are similar, we can start setting up ratios and proportions that are the same. So AC, the height of the person, is going to be proportional to the height of the pineapple. That is going to get set equal to the length of the person's shadow being proportional to the length of the pineapple shadow. So the heights and the shadows are proportional to one another. AC is 64, DF is what we're looking for, BC is 24, and EF is 105. So we just plug everything in, and then we cross multiply, and after you cross multiply, you find that DF is 280 inches, which is somewhere over 20 feet tall. Now, the next topic to cover is scale drawings. So let's go ahead and get rid of this, and let's read the problem. A scale drawing represents an object as smaller than or larger than its actual size, and you see that all the time with maps. An example here is a map with a scale of 1 centimeter to 1,500 meters. And 1 centimeter on the map would represent 1,500 meters in actual distance. So in example 2 here, we have a scale of downtown Dallas on a map where 1.5 centimeters is 300 meters. So we're going to take our ruler and we're going to verify that scale, and then we're going to find the distance between Union Station and the Dallas Public Library and set up a proportion to find the actual distance. So here I've got my ruler. I'm going to drag my ruler over and verify that the scale is indeed 1.5 centimeters to 300 meters. So now that I have that verified, I'm going to take my ruler and I'm going to rotate it so that I can find the measure between Union Station and the Dallas Public Library. And it looks to be about 6 centimeters. So now that we know that the length here is 6 centimeters, I'm going to set up my proportion. So for 6 centimeters on the map, we have some distance in real life. We're going to set that equal to our scale. Our scale is 1.5 centimeters on the map to 300 meters in real life. So here we're going to cross multiply. You get 1.5x is equal to 6 times 300, which is 1,800. And then divide each side by 1.5, and you get that the distance is 1,200. But again, you have to put in your units. So let's create a short word answer to solve this problem, or to cap off this problem. The distance between Union Station and the Dallas Public Library is 1,200 meters. So we did that with a scale map. What about making a scale model, very much like the boxcar that we had previously talked about? Well, the Lincoln Memorial in Washington, D.C. is approximately 57 meters long and 36 meters wide. We're going to make a scale drawing of the base of the building using the scale of 1 centimeter to 15 meters. So the first thing we need to do is set up the proportions of our length and our width. So we know that the length of our scale is going to be some length, L. And we're going to compare that to the real life length. Well, the real life length is 57 meters. That is going to compare to our scale of 1 centimeter to 15 meters in real life. Cross multiply, 15L equals 57, and you're going to get L is 3.8 centimeters. We're going to do the same for the width. The real life width is 36. We're going to compare that to our scale just like we did with our length. 15W equals 36. So our width is going to be 2.4 centimeters. And so now we're going to use a ruler to draw a rectangle with these dimensions. So here's my ruler. I'm going to start with the length. So I'm going to draw my scale over here. My length is 3.8, so I'm going to draw a line. That is about 3.8 centimeters, which would be right here. And then I'm going to take my ruler and I'm going to rotate it. And I am going to draw my width. Okay, so here is my rotated ruler. I'm going to just bring it over here. And I'm going to do my width of 2.4 centimeters. So let's get that. 2.4 would be about here. And then I can just finish off my scale from there. Okay, so that takes care of my scale drawing of the base, and of course I'm going to want to label it as well. So we have 2.4 centimeters as our width, and we have 3.8 centimeters as our length. Let's finish off this section talking about triangle ratios, perimeters, and areas. So just as you saw with the scale drawing there, we can compare our lengths and our widths. We can do the same with our perimeters and areas. So here we have triangle ABC similar to triangle DEF. We can compare the sides and get our similarity ratio, which in this case is 1/2. The perimeter ratio, if we take our perimeter of our small one to our large one, we find that the perimeter of ABC is 12 and the perimeter of DEF is 24. That ratio is also 1/2. So you can use your similarity ratio to find an unknown perimeter if you know the perimeter of one of the two triangles. Now for area, that's going to take a little bit more because the area of the first triangle is 6 and the area of the larger triangle is 24, which is 1/2. If you rewrite that, you can write it in terms of 1/2, well, that's 1/4. You can rewrite it in terms of 1/2 by doing 1/2 squared, because 1 squared is 1, 2 squared is 4, so that gives you 1/4. So to use the similarity ratio to find an unknown area, you have to use the square of the similarity ratio. This comparison is presented here in the proportional perimeters and areas theorem. So everything I just described is right there in that theorem. So let's take a look at an example, because it's really not that difficult. So first thing you got to do is find the similarity ratio. So the similarity ratio between these two triangles is going to be our ratio of 16 to 20, because those are our similar sides that we're going to compare. So our similarity ratio is 4/5. So we're going to use that to find perimeter and to find area. So let's start with perimeter. We are going to compare the perimeter of 36 on our smaller triangle to the perimeter that we don't know off of our larger triangle. And we use our similarity ratio just straight the way it is. Cross multiply, you get 4p equals 5 times 36. And eventually you find that p, once you do the math, is 45 feet. Now to find the area, you are going to take the 48 and compare that to the area we don't know, but you're going to have to take the 4/5 and you're going to have to square it. So before we can cross multiply, you have to do that squaring. That's 16 over 25. And then you can cross multiply. You get 16a is equal to 25 times 48. And you finish off the math and you get that the area is 75 square feet. And that's how you find the perimeter and area for the second triangle when you're given the first, and you can find a similarity ratio to work with. All right, that finishes off this section. In the fifth and final section of this unit, we will talk about midsegments.